赵佳琪、崔家园、陆一凡、姚如歌、李宗浩、Ricky、全南、丁、那、蔡家峰、Lexi。Okay, from this week, we're gonna start on the detection of targets. It is classified to be it can be classified to be two kinds. The first kind is the foreign target. And such like the target, it can be regarded as a point when it is self-contained, such like the car or the target. And another kind of target is called a distributed target. It can be self-contained. Another kind is distributed target. Third kind of target is it has a large volume, alright? So sort of like the terrain. For example, for the terrain radar or the meteorological radar, and the target that it needs to detect is expanded and distributed. So first thing we're gonna do is just set up the coordinate system. And for example, if we have a Cartesian coordinate system, y and theta. So, for example, if we have an electric field which extends or propagates along this direction, this direction. This is theta, and sorry, no, not theta. This is k. Direction k. So it's along that direction, and its shadow on the x or y plane is along this dashed line. This dashed line. Okay, and so it has the shadow on the x or y plane. So now we define as the direction of an electric field. The first one is along the it's parallel to the x or y plane, and also perpendicular to the direction of the propagation constant k. So it can be defined as this direction. We call it h, vector h, unit vector h. And also another part is perpendicular to the h, the vector h, and the vector k. Alright, so it's on this direction. We call it a vertical direction here. So that means on this, for this dashed line, it also has unit vector h along this direction. They have the same direction here. This is just the shadow on the x or y plane. And this angle is called theta, alright? Elevation angle. And or can be called the azimuth angle. And this angle is phi. Okay, now if we wanted to express the electric field, so first thing before that, we take a short review on that. So previously, we introduced the expressions for an electric field. For example, in the x or y plane, x, y, and its theta plane is out from the plane here, and if we have electric field, this one, so it's shared on x-axis is Ex, on the y-axis is Ey, alright? So the electric field can be expressed, it propagates along the theta direction, it equals x, right? Ex theta plus y, Ey theta, alright? Can be expressed by this one. And the Ex and Ey are phasors, right? So it has the Ex node, that means the electric field at position theta equals 0 times a propagation term, this one. And the Ey, the same thing, right? The initial amplitude or the amplitude E minus j k theta. Okay. Okay. So now Ex and Ey, Ex node and Ey node. For the Ex node and Ey node, it is amplitude. They are both are amplitude. And complex is complex value. So if we want, it contains the phase vectors, right? So previously we set for convenience, because Ex node and Ey node, it equals Ex, right, times a phase vector, right? And Ey also a phase vector. But here we assume the x component is initial phase is 0, so the E minus j or Ej phase is fine. It's 0, so it's plus 1, so this is Ex. And the initial and the phase vector, the phase part of the Ey component is defined E minus Ej delta. Alright? So delta is the phase difference between Ex node and the Ey node, alright? And Ey node. So when we try to define the polarization configuration, so it depends, or sometimes it depends on the values of delta, alright? So for example, if delta equals node, or it equals pi, that means the X node and Ey node in phase or out of phase. Alright, so under certain conditions, it should be a linear polarization. And secondly, if third equals plus minus pi over 2. And also under the condition that ax equals ay, okay? And so it becomes a circular polarization, right? And when it is positive, it means it is left-handed. And if it is minus, it should be right-handed, alright? You remember about that? And then this third part is the elliptical, alright? Elliptical pole. Polarization. So we defined an ellipticity angle. Ellipticity angle, and we call it chi. Alright, and the chi is related to the axis of the ellipsoid. So, and also we define an auxiliary angle tangent alpha node. Alright, so we're gonna use it here now. Then we come back to this figure here. So the first thing is we define the V component and H component. The same thing is we can express our electric field, alright? So the electric field E, it propagates along the K direction. So of course the V, EV plus H, alright? Then there is a phase vector of the propagation constant K times the unit vector dot product the propagation of the distance vector here, a unit vector between the target, the source and the target. All right. So R is the distance between the radar system and the target, and here we just choose the unit vector about it. So now, if we want, so we set the system of coordinate system of VH and H and K to be the spherical coordinate system, and it can be related to the Cartesian coordinate system, right? X, Y, and theta. So here, then we can define them, transfer them from the X, Y, theta Cartesian coordinate system to the spherical coordinate system. So K can be expressed as, so the X direction, that means is how much? Sin theta cosine phi, alright? And plus the Y direction is the sin theta sin phi, alright? And then the theta direction cosine theta, alright? So, but here, because they are in this almost the same direction, so they also a plus cosine theta. My big one. And how to define the vector of H and the vector of V. So H equals because in this the K O theta plane, the H is perpendicular to this plane, alright, the normal direction. So H equals according to the right hand rules, theta cross k. All right, then divide by its magnitude, like this one. Am I correct? Let's take it to a plane relation about that. For example, this is k. This is theta. This is O, this plane. And the h, the direction of h is outside of this plane. Alright? So we can take the cross section of theta cross h. This cross theta cross theta divided by their magnitude, then it becomes a unit vector. And then it equals, after the calculation, x sin phi plus y cosine phi. And for the expressions of v, it is much more easier, right? So it's much easier, it equals h cross k. And then it becomes x cosine theta cosine phi plus y cosine theta sin phi minus theta sin theta. Yeah, that's correct. So then we get the transformation from the xy theta, the Cartesian coordinate system, to the VHK, the spherical coordinate system. Then we can express our electric field to be a matrix. We use the matrix to express our electric field. For example, the electric field can be expressed as the EV and EH. Alright, so it's this one. And for both components, as we compare here, there is a phase factor, right? A propagation phase factor. So it's also associated in here, but we do not write it because to simplify the expressions of both equations here. And then, according to the expressions for the phase component and the electric field or the magnitude, so this term, it can be expressed as AX, AV, and this is H, E, J, dirt, the phase vector, like this one. So we get the expressions for the electric field here, and the AV or AH equals the magnitude of EV or EH, alright? So this is the expressions for this. So now if we wanted to say the polarizations or the ellipsoids of the ellipse class, so what we should do is we set them in the system. So perpendicular to a plane, define a plane perpendicular to the direction of the this is a dot. Okay. Dot here. This is the direction of K. It's outside of the plane, alright, perpendicular to the plane, normal to the plane. And this is V. This is H, the unit vector. So the electric field, the tips of the electric field are lungs. this direction, all right? So then it's along this direction. We define its axis or its dimensions is a psi, and along this direction we call it a eta dimensions. So we set. Let me take it be longer, and we call this one is psi, and extend this part. This line as eta. So axis, a new axis. Okay. So it has arrow like this. So now, if we want to take it to be its shadow on the. So now, if we want to get the AV and AH, what we should do is we take it to be its shadows on the both sides of that. So that means what we can do is maximum of each. So maximum of each. So that means this part is AH. This part, this shadow is A. Wait. So we defined two angles. The first angle is the angle defined by this part, from this angle to this. So from V to psi to axis. So we call it as to be the psi here. So psi is the rotation angle. And also we have another angle is the cosine. So cosine is defined as another one. Enlarge it to the shadows here. So this is A also. It's minus A. Okay. And so it has a direction here. Like this one. And it's actually should looks like this one. So there is this one. So now another angle is this angle, which is called chi. Psi and chi. Chi is called elliptic angle. So it's identical to the pattern we previously introduced here. So the tangent to psi and the tangent to chi has their own expression, right? Tangent to r node times cosine theta. This one is tangent of the sine to r node times sin theta. So the expressions for them. And alpha node is the auxiliary angle. The auxiliary angle is defined as tangent alpha node equals AH divided by AV. So that means the alpha node is AH divided by AV. So H equals the direction of, okay, this angle of a node, okay, is not equal to psi. So this is the now if the delta is 0 or pi, it becomes a linear polarization, right? So this one is a formal expression for the polarization of the electric field. And if the AV equals AH, then it becomes a circular polarization also if delta is plus or minus pi over 2. So now, if we come back to the scattering by or the incidence of the electromagnetic beam onto the object, so now if we have an incident beam, assume it's a plane wave, right? So then there is a target, it's like an aircraft, maybe. So, an aircraft here. And after that, it's gonna scattering, or there should be scattering around it, right? So some parts be detected along this direction by our radar system. So this is the scattering beam. Now, if for a plane wave, we define its electric field as in this direction, EI, instant beam, and the scattering beam, this direction, right? Be ES, this direction. So this is the electric field, and so this it should be noted that the shape and the orientation of the target or the aircraft is related to the scattering beam, right? So it's also, so when we detect the scattering beam, it's not only depends on the instant beam, it also depends on the characteristics of the target. For example, as dielectric constant and conductivity of it. So now, if this is the as scattering as always along many or the whole area around the target of the aircraft, and we should define two kinds of that. So the first kind is if the target is here. This is target T, and our antenna, we just use a whole antenna to represent that, okay? And another detection antenna is along this direction, okay? And so repeated and received like this one. This is the transmitter, this is the receiver, and the microsat configuration is as bi-static radar or bi-static configuration. And sometimes, or most of it, what we used is like this one, right? The transmission and the detection comes back, and so we have the transmitter and the receiver together or integrated, right, by using a duplexer here. And because such kind of configuration is monostatic. static radar or monostatic configuration. The monostatic, we can also call it a backscatter, right? So the first one is bistatic scattering. It really scatter the scattering components is forwarded, and sometimes, and another one is for the radar system, the actual radar system is the backscattering to get the backscattering components for that. So these both components of both configurations should be conducted separately for their expressions. So for the first one is we call the quality system configuration for this part, or the alignment for this part is FSA. It means as forward. Scattering, alignment, and for this term we call it BSA. It's back scatter alignment. So there are both alignments, and we gonna introduce them for the detections, the algorithms of the detections. So for the forward scattering system, so we assume there is small target. Okay, and S Y direction, X direction, here. So for our radar system, so there is the signals comes along this direction, right? Here. So it's univector KI along this direction to the target here, and it's the shadows on the X or Y plane is along this direction here. So we assume it has the V component, or its horizontal component should be along this direction, right? Horizontal H, and also the V component this direction here. And after the target, this angle is the incidence angle I. After that, it was scattered away from the target, and call it KS, the scattering component, the propagation direction of the scattering component. And we have antenna here. Okay, so there is antenna also. Okay, and so as X component or as parallel component, the horizontal component is along this direction. So it's a little hard to express that, but it should along this direction, H, and there is the V component of the direction over here. So this angle we call it theta f, the scattering angle here, and also because the this line, we extend this line. Okay. So we extend this line over here. So now we get the angles for the angle phi for the instant B is phi, and the angle phi for let me change it. Forget to get the shadows for this part. So the shadows for this part is the x or y plane. Okay. And this is the shadow here. And so angles for this part. This angle is phi s here. So now we can get the expressions from the according to the previously the expressions like expressions is this one, alright? So now we related to the instant part, and also related to the scattering part, right? The subscription should be changed. But here we need to take care as previously we said the direction of ks along or almost along the direction of theta, but here as the opposite, right? So that means is unit vector pi, hi, and vi should be a little bit different, right? So on the x-axis, the same thing, x cosine theta I, cosine phi I plus y, cosine theta I, sin y I. Previously it's plus, but now here it's minus theta, sin theta I. All right. Sorry, I think I mixed something wrong. The x-axis should be theta I, or it should be sin theta I, cannot be cosine theta. The x theta I is here, so the shadow here should be sin theta I, alright? So theta sin theta I, so this is theta cosine theta I here. And also come back and check this part. This part is correct. Okay, and now this is k and h and v is the same thing. H is called minus x sin y plus y cosine yi, and the vi equals the cross section of hi cross product between hi and ki, right? So this expression is around x cosine theta I, cosine phi I, cosine theta I, cosine phi I, minus y cosine minus y times cosine theta I sin phi I minus theta sin theta I. So the expressions for this part, and this is for the instant part, and for the scattering part, the ks expressions ks, hs, and vs. So vs is easy for us to hs cross ks, right? And hs equals the same thing, theta times ks, right? Theta times ks, and divided by the magnitude of theta times ks here. The only difficult part is the ks. But for ks, it's the same thing because it's outside this one part, and we have the expressions for the phi s and the theta s also. So the x component sin theta s cosine phi s plus y sin theta s sin phi s plus theta cosine theta s. So this is the expressions for the scattering component here. So when we compare that, we can see that when we want to transfer, for example, forward scattering, we can we want to set the relationships between the scattering component and the directions of their unit vectors. So, for example, for a forward scattering, what we usually set, the first thing is we want the instant beam and the scattering beam, all the scattering components are in the same plane, alright? This the same thing. If you take measurements on that, you already think that, and you can already find that if they are in the same plane or on the same plane, that means you can get the maximum scattering components in that plane. So that means our instant beam, because here we can see that the instant beam is the corresponding angle on the shadow on the x or y plane is phi I, alright, and the scattering beam is the shadow on the x or y plane. Its corresponding angle is theta s. So that means if both are should be in the same plane, that means phi I equals phi s. Alright, so this is for the forward scattering, and also the x or y plane, then that means it can be, or the configuration or the alignment, it should be simplified here. So that means now the relationships of the Vs, Vi, and Ks, Ki, and Hs, Hi should be obtained here. So firstly, we can usually set the direction of Vi equals Vs, and Hi equals Hs, and Ki equals Ts, because they are forwarded. So we can obtain the expressions for this one, these things. Oh, and also the direction between the theta I and theta s. Here is, I lost the expressions for this one. Theta s equals pi minus theta I. So according to these two assumptions, if you substitute them into this equation group, and you're gonna obtain this equation group here. You can try that. So this is for the forward scattering alignment. Now, if we want to get the configurations for the backward scattering alignment, what we can do is, so okay, let's take a short break. We're gonna come back later. for the backscattering alignment. So, firstly, as we said, we use just one antenna, to collect to radiate and then collect the signals or the beams. So, but for the simplification, we separate them together. So, but we set the direction of the received signal is towards the target, because then when we transfer the coordinate system from the Cartesian to the spherical, its direction gonna be then forwarded back to the transmit antenna here. So now what we can do is, the first thing we can see is for the transmitter side. For the transmitter side, we use the KT, not KI now. We use KT and HT and VT. So here we can see that it's the same thing with the forward scattering alignment, all right, for the at the transmitter side. So we can get the expression. This is HI, this is VI. So it means KT equals KI, and HT equals HI, and VT equals VI. So the same expression for that. And for the receiver side, so we define KR, HR, and VR. All right. So we can, when we compare that with this side, it means KR equals minus KS, right? So because it's backscattering, so KR equals minus KS, previous KS, and HR equals also the minus HS, but VR equals the same thing, VS. Expressions for that. It's because when it's electric field, after the reflection or scattering by a target or by plane, if there is a no phase change due to the surface of that, then on the surface of the plane, the electric field should be continuous, right? So the parallel part of that. So this is the expressions for the backscattering component here. So now what we wanted to do is we want to use a matrix to connect the transmitting side and the scattering side. Also a matrix to connect the transmitting side or the incident side and the scattering side. Also connects the transmitting side and the receiving side. So we use a scattering matrix here. So the scattering matrix exactly describes or contains the shape or the properties of the target, right? Because it's transferring the coming signal to the output signal, right? So it's related to the target. So that's what we usually sometimes we call the RCS, right? So RCS is usually obtained, not equals the scattering matrix, but it is obtained by using by obtaining the scattering matrix here. So we use the matrix S and S. So the first one, the matrix S, is for the forward scattering alignment, and this S is the back scattering alignment. So we want to separate them, and also find some relationships between them. So we take it firstly now. We define our electric field. So for the previously as we define it, EI equals the alright, EH by using a matrix, right? So also the ES simply we define it as EIS, So now, if we want to get the expressions from S equals the matrix times EI, right? So that means ES equals matrix times EI. Right? So the conversion between both, I think, is easier for you guys. All right? So it is a 4 elements matrix. All right, 2 by 2, and the first one is, we can see, is from V to V. All right, from V component to V pole, or we call it S, from V to V. Okay. And also the second term is from H to V. All right. Is it correct? From H to V. So S H to V. So this term is from V to H. All right. So this is from V to H. And this term is from H to H. So we can get the expressions from all these terms and combine them together and convert that. So now we can get the expressions based on that one. And also, because previously we set our instant beam is a plane wave, so all the lines are parallel to each other, and for the scattering, after the instance on the target was scattering, the scattering component, we set it to be a source for spherical wave. Cannot be plane wave, spherical wave. It's related to the transmission distance between the target and the receiver, and also this term is E minus J K A R R. All right, so it's related to this term. So for spherical wave, the propagation factor. So here is what this one is. S. Then times a phase vector. Here. So this is the expressions for the electromagnetic field. And another thing that we wanted to say is, if the we wanted to say each component for the scattering matrix. So now, based on the coordinate system here, so this one is related to all these components, theta I, phi I, and also theta S, phi S. All right, and also the another two angles is theta J, J. These two terms. So the theta J and phi J are the orientation angles of the target. That means the orientation of the target. So previously, usually we said its normal direction is along the theta axis, but sometimes it's not, right? It has its own orientation. It depends on itself, actually. So that means our scattering matrix is related to all these parameters. So if we want to get the expressions for each of them, for example, if we want to get, okay, this one is times R T minus JK, okay, and we want to get the component maybe S, we for example, and so it can be S equals E with S divided by E with I times minus JP. Alright? So we get such an expressions for it. Correct? I think so. Yes. So now we get the expression for this one. Sometimes we search because the direction of our or the position of our detection system, our radar system is far away from the for remote sensing. It is far away from the target, and we set it in the far field for RF tends to the infinity, and also that means the spherical wave can also be regarded as a plane wave, right? So then this one is the a more simplified expressions for that. So this is for the forward backscattering, the forward scattering, and for the backscattering, we set it to be all these terms is instantaneous becomes transmitted term, right? Transmitted term, and the scattering term is the received term. Received term, same thing. And what we can obtain previously or here, if we assume, previously we said that the EI equals ET, alright, we said the same thing, but the ES is related to ER. There is a relationship between them. We can get that. And could you know how to? Obtain that? The ES and ER, the relationship between ES and AR. three segment, the V component equals to each other, right? The H component is minus, right? So that means the V component minus 1, right? So that means this one is ET V, ETH, right? A matrix, a 1x2 matrix, and this term is this term is EVR, EHR, right? So the H component, the V component equal to this direction does not change. So that means it's unit 1. And the H component just a minus, so it's minus 1 here. So when we combine them together, we can transfer that just based on their unit vectors, right? So now we can express, or we can get the expressions for the backscattering alignment just based on our conductions for the forward scattering alignment here, but just transferred each term and for the instant part and for the east part. But for this part, we can just using the scattering matrix and multiply or divide by this matrix, and we can get the expressions for its backscattering matrix here. And this is this part here. And finally, what we can do, so we get the x and times s here, and the matrix should be 1 node, so minus 1 here. So that's expressions for this part. So if you transfer because the transferring this part, all right. So R equals E. Equals Pi. So ES divided by this part, and this part is divided. So this is S equals this term. Yeah, it's correct. So it should be expressed like this equations. So we can get that the S V, all right, S H V H S H V S H H. It's related to 1 node of minus 1 times S V V S V H S H V S H H. So you can get the relationships between each element, right? Equals S V V S H H equals S H H. S V H equals minus S V H. S H V equals minus S H V. So we get this thing. So now we can see that for the come back to the backscattering scatter alignment here. So for the backscatter alignment, because our transmitter and receiver are at the same direction or along the same line, right? So the transmitter KT and this is the following direction KR, right? So they are along the same line, and so that means H equals S H V. This is the backscattering. And so until now, what we concentrated is for the electric field. And for the electric field, there is one thing that making it a little bit complicated is that it needed to obtain, also take the measurements on the face, on the face angle, right? So for the electric field, we need to take its magnitude. You can also need to take its the phase angles, all right? So what we can do to simplify that or make it a little bit more easier for the measurements is we want to introduce the intensities of that. So now there is a term as called a vector specified intensity. And we let capital I to represent the intensity here. And for the intensities, it is really related to the electric field, right? The square of the electric field previously, right? So now here is also related to both parts. So for the incident part, it is becomes, for the electric field, it is 1/2 matrix, and for the intensities, it becomes 1/4 matrix. So 1/4 is for the V part, for the H part, and for also U part, and for the also here. So for each part, it represents the V and H corresponds to the terms of the specified intensities, and U and V, capital U and V, are jointly accounts for the phase difference between the E, V, and the EH. So now from here, that means what we can do is, so the IV and IH corresponds to the intensities. So that means it equals EVI square, the intensity, EHI square. And another two terms is correlated to the phase difference. So the first part is EVI, EHI star, and we take its real part. And also another term is the same thing, EVI, EHI star, again, we take its imaginary part. And also, this is not exactly the same, all right? It should be divided by it, the intrinsic impedance. Okay, the intrinsic impedance of the medium or the target, and so this term is called, or this matrix is called Stokes matrix, or all these terms are called the Stokes parameters. And so now we get the expressions for the incident beam, and one can also get the expressions for the scattering beam. Alright, so now as what we did on the electric field, for the intensities there should also be a transform matrix, and so the IS equals a transfer matrix times I here, right? So this matrix is called a model transfer matrix or a model matrix. Matrix X. Muller is, I think that he's a German guy, so by his name, Muller. So, and also here, when we come back to this part, for spherical waves, we have this part, all right? But when we come back to here, so for intensities, it should be a absolute and square of that, right? So it becomes R squared divided by 1. This is for spherical wave. So previously the transfer matrix S, it is 2 by 2, all right? So this model matrix should be a 4 by 4 and matrix, and it is a little bit complicated, and I do not want to write it here. I think we can just combine them together and we can get the expressions for it. And also for the backscattering, also the same thing, just the matrix times IP, yeah. Like this one, and so this is the expressions for this part. And when we get these things, then what we need to do next, get the transformations for that, then we should know how to obtain the RCS, the expressions for the RCS, right? With a cross section. So now, if we assume that we have a transmitter and the target again, the transmitter side and the receiver side. So for the transmitter side, we assume our transmitted power Q, the transmitted power here, and also the distance from the transmitter to the target is RT. And the distance from the target to the receiver is RR. And also the received power is PR. So we use P and Q to represent the polarization. Alright, so we are not sure they are V or H, we just use them to express that. So, and the gain for the antenna for the transmitter side is GT. The gain for the receiver side is GR. Okay. Now, what we can do is reset. For example, assume that we have the transmitted power along the Q direction, the polarization. Okay. And it is propagates as a spherical wave, and when it reaches to the target, its power becomes, its power density, if we want to get, divided by 4 pi RT squared. Alright, the power density reached to the target. And also, it has S gain GT. Same thing, alright? And then, after it reached or it launched onto the target, then it was scattered away, alright, to the receiver side. So we assume there is another term as the radar cross section, sigma, and S incident is Q, output is P, polarization, so it's P, Q. So, and so it's radiated out now, and it's collected by the receiver antenna at the receiver side. All right. So the first thing is it has antenna gain GR, right? For the reciprocity of the antennas, we assume they are maybe category antenna or the whole antenna. It's expressed like this one. All right. And after it's launched away from the target, or scattered away from the target, and propagates over a distance of RR. That means we can set for each elements small sources, and that it radiate the spherical waves, right? Consider it as spherical waves, so it is 4 pi r square, like this one. So combine them together, connected by this term, and then we can get the expressions for the antennas. And until now, as we all see that this is the power density, also all right, divided by this term. So what we should do next is we want to get the exact power, and so it should be times the area of the receiver, all right? The power density times the area of the receiver, and then you're going to get the expressions for the received power at the receiver side. Is that all? Power density, maybe previously we use S. SNEP. Let's press it, alright? But it times the area, it equals P, right? Is that all? Is that all? It's not, alright? Because as we previously mentioned that it has, for the antenna at the receiver side, it has radiation efficiency, right? So these terms together times this part. And the psi r is also related to the antenna gain at the receiver side, all right? It depends on the psi r times directivity of the receiver's antenna. Also, that's one. If you forget that, just go back to the previous courses and check with that. So now we can get the received power, or the received power, R to represent that. So now when we put P divided by QT, we can get the expressions for the GT R. Right? And divided by 4 pi r t square. Alright, and also times the radar cross section sigma q, and also times the r psi r. So for the AR and the psi r, the relationship is AR. It can be expressed as lambda square over 4 pi dr. Alright? You remember? And the JR can be expressed as this one. So psi R times AR, psi R. So you can get another expressions for the antennas, right? So now finally we can get the expressions for the sigma PQ. It's related to the these terms, right? So these terms, it means it's related to the antenna properties and the transmitter resource and the for a radar system, and related to the JT equals GR actually, alright? They use the same antennas and equals J here. So and the RT equals RR, it equals the distance R, right? So that it is only related to the configuration of the radar system, the target, and also related to the transmitted power and the received power here. And so if we relate them together, then we know we can get the radar cross section here, right? So the radar cross section is usually can be used to reflect or to obtain the properties of the target here, and its expressions. There's also it has its own expressions based on all these things, and we're gonna introduce later in the following chapters maybe. But what we can do is definitely related to 1 over the fourth order of the distance between the antenna and the target. So this is for a point target. All right, we usually set the detections, the detection that we usually set all these things to be a point here, and we positioned the target at the origin of the Cartesian coordinate system. But actually, if the target is distributed, so that means for each element, what we can do is we can only set, for example, there is target here. So our expressions for previously for this part is this element, and for this part, this element, and both elements they maybe have a different elevation angle. So this is I, this is J, for example. I, theta, J. They have this different elevation angles. That means the expressions for the radar cross section should be different. And what we can do is, so previously we can get here, we get the radar cross section PQ for the whole target, right? For the whole target, because we set it to be a point. But for the target, it has distribution. The sigma PQ cannot be used, all right, because it also angle dependence. So what we can do is we set. There is a node here. A node. We just use the back scattering coefficient. Name it as backscattering coefficient equals average of the whole distributed target divided by its area. It's like that one. So that means now we get the expressions of the backscattering coefficients for each small elements. And then add them together. Or take the average of that. You can get the total part of that average cross section. So for that part, that means the expressions for each part, we need to take an integration on it. So that means we needed to take an integration on it and get the total with a cross section of the whole distributed target here, and that's why what we need to. That's why we think it is difficult to obtain that. For an example, so here is a plot. The radar cross section, the scattering pattern of a plane. So we can see that when we take measurements around or the circle of the plane with the plane in the origin of the circle or the center of the circle, we can see its RCS is gonna be different, right? It varies, we change all these things. So that means there is for different parts of it, it's gonna get a different radar cross sections based on to the its shape and also its material. So now, if it's set it, for example, if we set it to be a point, that means we can only get the average value of that one. All right. So this is for the plane, and we can see that its cross section can vary sometimes from maybe 5, 10, 15, 20, 25. Okay, maybe it's from 5 to 30 dB. All right, there is a lot of difference, around 25 dB, and this is for the plane here. And also, if this is a point target, if we see this plot. So this plot is the measurements. So this plot is the measurement on the asphalt ground detected by a radar system, and from the researcher's point of view, they see that the ground is uniform and they are always the same ground, but just when it changes its position a little bit, you can see its measured backscattering power. It varies, it fluctuates always. That means even though we think, or we can say they are uniform sometimes, but the backscattering components, the backscatter power fluctuates a lot. You can see sometimes it can reach to minus 40 dB. And that's because when they back to see the texture using imaging here, so this picture. So you can see that this is a soil road here, and when they take pictures and enlarge that picture, you can see there are many. You can see the exact textures of this surface. So that means such a kind of texture is going to lead to significant fluctuations on the on the target, of the distributed target. So that means if we want to analyze the backscattering information or the radar cross-section of a distributed target, we need to take statistics analysis on that. So that's what we're gonna introduce next week. Okay, then see you guys next week.
Actually, I'm a day scholar, that's why I got late.
Okay.
Thank you.
哦，你可以站起来说。这个是吧？
这个有没有参考书呀？
这个没有参考书，然后，但是我在里边发了一些参考书，你可以，我应该在里边发给他们，发给了他们2本，往上翻一下，你应该能看到。上面看不到。哎，你为啥看不到？
哦，对，
他应该可以看那个聊天记录，就是前面聊天记录。
行，蔡老师。